I'm Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth. Hey y'all. Welcome back to our AP Physics 1 curriculum. Still in Unit 1. We're on 2D motion still. And this is our angled projectile problem. So we thought we'd do an example of that with the whiteboard and show some concepts. Okay, so we're just going to jump in right here. I have our big three that we're used to seeing. I've just added that y for vertical subscripts. Our v final equals our v naught, initial velocity in the y, plus our acceleration in the y times time. You've seen these other two, but you know that the y's all mean vertical, so these are our vertical. But now I've also have an x, a horizontal, because remember we talked about this. Go back and watch the concept videos on projectile motion if you're confused, but we keep that horizontal and that vertical direction completely separate. The only thing that's the same in those two directions is time. All right, but I have one of my big three. The only one that does us any good is that this final position in the horizontal direction equals that initial position in the horizontal direction times that initial velocity horizontally times time. And then, of course, the equation on your review sheet, on your AP equation sheet, is plus this 1/2 a times squared. But remember, this acceleration is not our y acceleration, our vertical acceleration, which is due to Earth, negative 9.81. There is no acceleration in the horizontal direction in these projectile problems. So really, this equation just looks like this. I keep all of the subscripts. I know it looks kind of confusing, but they will keep it separate from the horizontal to the vertical. And then we have one last formula here, which is our range formula. We like to call that the range formula. Range meaning if Mahomes threw a football at 10 meters per second at an angle of 20 degrees, range would be from where he threw it to where his receiver caught it. In other words, range is how far did it go. That is your v naught squared, and that's going to be your total. There's no y or x here indicating vertical or horizontal. Because of how this is derived, you're using your whole velocity, the hypotenuse, and then squared divided by little g, which is like acceleration due to gravity, only that's a vector. This is a scalar quantity, so it's just 9.81. Times sine of 2 times your angle. In this case, it was 20, so 2 times 20 would be 40. It'd be sine of 40. All right, so that's kind of, that's the start of that. Those are the equations that you're going to need for projectile motion. I'm going to go over here and start at the cross, and I'm going to start identifying my variables. The first thing I know is that I have a ball that's kicked off the ground at 10 meters per second at 20 degrees. And then it says, here's your little note. This is your star. It's your big red flag, although I did it blue, but it's your red flag. It takes off and lands at the same height. That means that you can use that range formula because that is a condition of how it was derived, that it must take off and land at the same height. All right, so I'm going to get started. I know my v naught is 10 meters per second. I know that my theta, or the angle, is 20 degrees, so there's my magnitude and my direction of that velocity vector. All right, and then I know that I want how far. Well, now this goes back to that video we did way back in 1D motion about the clues in word problems. How far always means your delta x. All right, that's going to be in meters when we find that. And then it wants to know what was its how long was it in the air. How long means time. So that's going to be time in seconds when we find that. And then what was its max height? That's going to be its delta y. All right, and that's going to be in meters when we find that. They want three things. All right, first of all, they want delta x. That's the first thing they said. How far did it travel? Right here. All right, I saw this big red clue. It takes off and lands at the same height, so I'm going immediately to range. That's a handy dandy formula, so I'm going to rewrite the formula. Always rewrite the formula. I promise you, I know it takes a second longer, but it will save you from missing all these squares. If you can look up at the formula, it's going to save you in points. And oftentimes you will get a point of credit if you've identified the correct equation or plugged something into the correct formula, the correct equation. So you will get points for that on those AP free response problems. So here we go. Now that I've identified my formula, I have identified all of my variables. I'm just going to get started. All right, I'm going to do a plug and chug now. My V naught is 10. Now this is the only place that you can use your whole hypotenuse. If we're talking about initial velocity in the y, you've got to use that V naught sine theta. If you're talking about your initial velocity in the x, you've got to use that V naught cosine theta. Because if you took this, let me draw it up here, if you took this 10 at 20 degrees, then your V naught in the x is V naught cosine theta, and that vertical component is going to be V naught sine theta. All right, in other words, it's not 10 in either one of these directions. It's 10 in the hypotenuse, but part of that was in the horizontal, part was in the vertical. Go back and watch the concept videos if you're confused on that. We do have a video on that, on breaking a vector into its components, and also in our projectile motion concept video. Okay, now, G is 9.81, it's the scalar version. Sine, it's going to be 2 times that 20 degrees. All right, which is going to be sine of 40. If you go and do this, you're going to get a delta x of 6.55 meters. And I'm going with 3 sig figs here. And all I'm going to do is do sine of 40, multiply it by 100, and divide by 9.81. Okay, that's going to be 3 sig figs because I have a 10.0 here and a 20.0 here. So I'm going to go with 3 sig figs. All right, perfect. Now, that's done. Check. The next thing it's going to ask for is how long was it in the air? Okay, you've got a couple of choices here, and here's the deal. Don't stress about it. If you've got the variables you need, then you're going to get the same answer. So in other words, I'm seeing time in this first one. I now know my final position. It was 6.55 meters. And then I know my initial because you can start all these problems at 0 meters in the x direction, and then I know it goes 6.55 meters. So I know that. I know my initial velocity in the x because it is 10 cosine of 20. And then I want my time. And that would be the whole time because it's from here until it lands on the ground. So I could use that formula. So I'm going to do that. So I'm going to switch colors here to red, and I'm going to say, hey, I'm using this first one. My final position in the x equals my initial position in the x plus my initial velocity in the x times time. Well, my final position was 6.55. My initial was 0 because I can call this 0 where I start the problem. And then I have my initial velocity in the x, and this is where you can't just plug in 10. It is not the whole velocity. It's only this part. V naught cosine theta times my time. All right, so now I'm going to put in some little numbers here. V naught was 10. Then it's going to be cosine of 20 because my angle was 20. That theta just means the direction or your angle times time. And I'm going to get a time of 0.700 seconds. That's my whole time in air. You're like, but wait a minute, why didn't you use this one in the y direction? Okay, you absolutely could have. There's a little concept there. Let's do this. Let's say that I use that second one. And I'm going to use the second one instead of the first. Okay, so I'm going to go back and erase actually all of this so I can finish up the problem. All right, and remember that was 0.700. So you're like, well, wait a minute. Why couldn't you have used this second one and do time in the y direction? Absolutely could have. Look at this. I have my final and my y equals my initial and the y velocities plus my acceleration and the y times time. Now, what I would do in this instance, if you want to use the y, is I would only do this part where it gets to the top, the up part. All right, so I'm going to say up. So if I do that, I know my final velocity is 0 because in the y direction, again, go back to concepts if you need this, but in the y, it's just going up like a free fall, stopping and then turning around and coming right back down in the vertical direction. So when I'm going up, my final is going to be at this top. So it's just going to be up. And my final is going to be that final velocity in the y, which is going to be 0 because we know it stops to turn around directions at the top. So this is just going to be going up only. So 0 is my final velocity in this part, and my initial, you cannot put 10 in. All right, 10 is the whole velocity. Only part of that is in the y, and that's 10 sine theta. Plus and let me go ahead and just put a variable in here. That was kind of messy. Let me just put my variable in here, and that's going to be v naught sine theta plus my acceleration in the y times time. All right, I'm going to take a minute to write this equation down. You never know at what point you might get a point for just having the right equation or plugging the right thing into that equation. All right, well, I know this is 0. My v naught was 10, my initial velocity, sine theta, which was 20 degrees, plus my acceleration in the y. We did not define that, we should have. Acceleration in the x is 0, and my acceleration in the y, just Earth is taken over, so it's negative 9.81, as it was in all of your free falls. All right, so I have negative 9.81 times time. Okay, if you were to do this, you're going to get a time that is approximately 0.35 seconds. And you're like, wait a minute, you told me I would get the same time whether I did this equation or this one. And I got 0.7 seconds here. Excuse me. That is only because we only went to up. If an object takes off and lands at the same height, then time up is going to equal time down. All right, and this is a concept. If it takes off and lands at the same height, then your time up is going to equal your time down. That means that my time up was 0.35. But then add that, my total time in air is going to be my time up plus my time down. That's going to be 0.35 plus 0.35, and guess what you're going to get? You're going to get 0.7 seconds, just like we did when we did the x. Now, why didn't we have to do that in the horizontal direction? Because in the horizontal direction, we started here, and we had gone all the way to the end. We used 6.55 here to find time, and that was the whole time in air. But in the vertical direction, we only used to the time up to max height. So you've got to add that time plus this time. But you get the same thing. All right, you just have to remember to double that. And it only works if you take off and land at the same height for that y direction. Okay, perfect. Now let's go and get the third thing. We have the third thing, what was the max height? Okay, well, I can use this one, and YF will be the max height, or I can use the second one. Again, it doesn't matter what you use. All right, as long as you put the right variables in. If you have all the variables except what you're looking for, then winner, chicken dinner, you can use either one. I'm going to use this second one, and I'm going, max height is right here at the top. So I'm going to do up again to max height. All right, and we love that because we know then the final velocity in the y is 0 because it stops to turn around. So I'm going to do this v final in the y squared equals v naught, or our velocity initial in the vertical. So that really means vertical velocity final and vertical velocity initial is what that means, plus 2 my acceleration in the y, delta y. All right, I have my equation. I can totally plug and chug now. All right, I know my final is 0 when we're going up to max height in this y. We know that's 0. We know my initial, it's not 10, it's 10 sine theta, and then you've got to square that whole thing. Do not forget the square. It's a very common error. All right, plus 2 times negative 9.81 times that delta y. Now, here's the deal. First of all, do not forget your calculator needs to be in degrees, not radians, or you're not going to get the right answers, and don't forget to do this square. If you go to solve that, I would subtract that over subtract from both sides, I should say, but it's going to be over here. I have a negative 19.62 here, and then I'm going to divide that, and so my delta y comes out to be 0.596 meters, and I'm doing 3 sig figs. So now you know the answers to this. How far it went was 6.55 meters, how high it went was 0.596 meters, and how long it was in the air was 0.700 seconds. All right, perfect. That is your angled projectile problem and the equations that you would use. And remember that range. The reason we were able to use that range is because of this lovely statement that it takes off and lands at the same height. Thank you for watching. Hope that helps, and happy physicsing.